So the plan is to understand each component of the modeling process. Remember that the modeling process is not really sequential. It is iterative in the sense that you go through a process, you determine whether your model is doing what you expect it to do or not. And then you go back to the beginning and refine it. And once again, evaluate how the model is performing. So the key steps may be visited multiple times. And this is shown in this figure. We have a real world problem that you want to model. In modeling it, there are these components you have to take care of. You have to define the problem correctly. You have to define the variables, okay, that you will need in order to design a model. You have to make assumptions. Perhaps you have too many variables. Make assumptions that will trim down the variables and just use the most important ones. Okay. And then this will also help you to define properly your problem again. Okay. All of this require research and brainstorming to see how best to develop the model. Okay. Once this is done, you would get a solution. The solution could be solving a function, discretizing the equation or system of equations, or using software to get a solution. Once you get a solution, you analyze the solution, or if you like, assess the model to see whether it's doing what you expect it to do. If not, you go back here and repeat this process by refining all these steps, okay? That is why it is not a sequential process, it's iterative, because you go back and forth, getting a solution, analyzing it. You're not satisfied with it, you go back here, refine this. So sometimes it can take years to develop a very good model. But once you get here, analyze it, and you think the model is doing something good enough, right? In terms of the process you want to model, then of course you then go ahead and report your results in different forms, whether it's a paper you're writing or poster, some kind of a presentation by talk to discuss the model and what it does. Okay, so this is an overview of the process of modeling, and I think this picture depicts quite well what all models go through. Okay, so each of the next few steps actually just elaborate on these ones. Okay, the same thing I've explained here, so they just elaborate on them. Define the real world problem, right? Because a real world problem can be quite broad and complex. You have to refine it and define it quite well. Okay, so refine the conceptual idea into a concise problem statement, which will indicate exactly what the output or the outcome of your model will be. Okay, for example, in the previous problem, what is the volume of plastic waste your town sends to landfills last year? So this is specific, and the model should be able to give you that number, right? And then making assumptions. So this is talking about this part, right? Making assumptions. Okay, so early in the work, the problem might look too complex, but if you make assumptions, you simplify the problem, and then you also help to sharpen the focus. Okay, so during this process, you reduce the number of factors or variables affecting your model, and then you decide the factors that are most important for defining the model. Then define the variables, the most important variables. You would look at the dependent and independent variables. In other words, factors that are influencing the phenomenon that you want to understand. Okay, so you should be able to list down those factors, quantifiable variables, maybe with specific units, all right? If it's temperature, if it's the mass, the concentration of something. So you should have independent and dependent variables, and sometimes you would have some parameters in the model. Okay. So in understanding these ideas better, you'll be able to both to define the model inputs and to create, relationships between the mathematical variables, which ultimately will result in establishing your model that you want to use. So this is just an example. You have, a dependent variable P, which is a function of like X and T. X should be space and then T is time. How that is changing with respect to time is governed by this, where alpha and K here are some parameters of the model, right? And H, alpha H and K here are some parameters. Okay, so you would come up with something that tells you how, if you like, the population of a species is changing with respect to time. Okay, then once you have, if you like, a crude model, of course, you then try to get a solution. All right. That is how you learn what the model is doing. And is the solution telling you that the modeling is answering the question you want to answer. Okay. So to determine the solution may involve actually, either analytically computing something, solving a problem, evaluating function, running simulations, solving an equation. Okay. Depending on the type of model that you're using. Okay, sometimes these days, real models will require that use some kind of a software, Python, MATLAB, Sage, different kinds of software to compute to get a solution. Okay. And then once you have a solution, you go back and you analyze it, right? You assess whether it's doing what you want it to do. What are the strengths? What are the weaknesses of the model? Are there weaknesses are there certain situations, right? When the model doesn't work. Okay. And you should make this plain. You should let people using your model know that these are the limitations of the model and how sensitive is the model, right? If you change the assumptions or change the model parameter, is it very sensitive from, very stable to like very, erratic model? Is it possible to make, at least point out possible improvements, right? Could something be done to improve it? For example, this model here was the original model for population growth, right? How population grows with time is proportional to the actual population, where arrow here is the growth rate. But this just gives you an exponential growth, all right? Which is not very realistic because things don't grow exponentially. There are factors, environmental factors that will limit the growth of a population. And so this was refined, this exponential or Malthusian model was refined to give you what is called a logistic model. And now this says that if a population grows beyond K, which is called the carrying capacity, then the population then begins to decrease. Because if this is greater than this, then this factor is greater than 1. So you get a negative, which tells you that P is decreasing with time. Okay. So determine whether, your model can be improved. And that is important. Okay, so once you are satisfied, after going through this iterative procedure, once you are satisfied with the model, you have to report your result. Otherwise, nobody will know what your model is doing. Okay, so you have to provide unbiased results. Or sell the model to some company to work on or to use it for their work, or write a published paper, abstract, a summary somewhere. Okay, so you have to report it or give a talk to colleagues, to a scientific community about what the model is doing. Okay, so keep this in mind. This picture is really what I've done is summarize this. This is an overview. So this is important you understand the various components of this, okay, that guide you in trying to develop a model or whatever model you want to develop or whatever process you want to study. Okay, so this will be the first part of CBAS210 and the modeling. All right, you have a series of videos. So study them and understand what is going on in there. All right.